Hello, my name is Walter Kucharczyk, and my lecture is on the basics of MRI physics.
I am a neuroradiologist from the University of Toronto. From the start of my career, I have had an interest in trying to explain the basics of MRI physics in an understandable and factually correct manner to a variety of audiences. In this regard, I was very fortunate to have met and worked with Don Pluis, an imaging physicist in Toronto. He and I first gave this lecture at the ISRM over 20 years ago and many times since, at the ISRM and other meetings. The talk has proven to be very popular. I am also indebted to Britton Pluis, Don's son, for having created most of the animations. This talk is intended to be an introductory lecture in a multi-lecture course. It is intended to provide a high-level overview of the entire MR imaging process. There is very little detail about each component of the process. The details are left to the subsequent lectures in this multi-part course. This talk demonstrates the MR imaging process from start to finish, starting with a single nucleus and ending with an MR image of the head. This is accomplished almost exclusively with a series of video animations. There are only 2 or 3 formulas in the entire talk. The process that will be described is that the body part that we wish to image, in this case the head, is centered in the MR scanner. The imaging process is initiated, and the end result is a set of MR images of the body part that we placed in the scanner. In a series of animations, I will show and discuss the physical properties of a single hydrogen nucleus and how these properties affect the behavior of the nucleus in a magnetic field, how groups of nuclei behave with respect to one another in different situations, and how these nuclei induce an electrical signal in a detector, what determines the total signal induced in the detection system, and how this amount of signal affects the intensity of a single voxel, in this case the single voxel representing the whole head. I will then move on and show how the source of the signal can be precisely localized to different positions from within the head. I will end the talk by reconstructing the signals that have been collected and produce an MR image of the head. The talk is 60 minutes long and is divided into 2 parts. Part 1 describes the fundamental principles of obtaining signal from the body part we are scanning and the main determinants of the amount of signal that is detected. Part 2 describes how the signal is spatially localized and an MR image created. The topics that will be discussed in Part 1 are the properties of the hydrogen nucleus. There are many other NMR active nuclei, carbon-13 for example, but hydrogen is the most prevalent NMR active nucleus in biologic systems, and it is the nucleus imaged in over 99% of all MR imaging. And it is the simplest to understand, so the entire talk is focused on the hydrogen nucleus. Both classic Newtonian physics and quantum physics can be used to explain MR imaging. In my opinion, classic physics adequately explains hydrogen MR imaging, and it is simpler to understand, so I will use classic physics principles exclusively in this talk. I will use classic physics to explain the formation of magnetization, the notion of resonance, how signal is detected, and how detectable signal is created. I will end Part 1 by discussing T2 Star, T2, and T1, and show how these tissue properties affect the amount of signal. Most hydrogen in biologic tissues is found either in the form of water molecules or fat molecules. For the most part, the hydrogen nucleus in fat and in water behaves very similarly, but not exactly the same. So let's look at the hydrogen nucleus in water. It has charge and it has spin. So charge and spin together give it the property of a magnetic moment. Therefore, an analogy can be made to a bar magnet. when placed in an external magnetic field, both the bar magnet and the hydrogen nucleus tend to align with that field. The hydrogen nucleus has one further property. It has the property of mass. Spin and mass together give it the property of angular momentum. So an analogy can also be made to a gyroscope. When a gyroscope is put in the gravitational field, it rotates around its own axis, but also rotates around the axis at that gravitational field if you tip it with your finger from its resting state. Similarly, the hydrogen nucleus, when placed in an external magnetic field, and if energy is imparted into the system, it will not only rotate around its own axis, but it will rotate around the axis of that externally applied field. That rotation around the external field is called the precessional frequency and is key to understanding the MR imaging process. It's called the Larmor relationship, and the Larmor equation states that the precessional frequency is equal to the gyromagnetic constant multiplied times the main magnetic field. If the main magnetic field increases, the Larmor frequency increases. That rate of precession will increase. We will now progress from a single nucleus to a group of nuclei. In this animation, 4 nuclei are shown, but it could be any number of nuclei because the concepts are the same for hundreds or even billions of nuclei. The direction of the applied field is shown by the white arrows at the top of the screen. This is conventionally called the Z or Z direction. Magnetization has magnitude and direction, so it is a vector quantity. When dealing with multiple vectors, vector math must be used, taking into account both the magnitude and the direction of each component vector. In this illustration, the 4 nuclei are shown lined up in the same direction as one another. When they are aligned in such a way, they are said to be in phase, and the overall effect is a straightforward addition of their magnitudes. If they were not aligned with one another, they are said to be out of phase, and their overall effect is less. The overall magnetization of the group of nuclei can be represented by a bulk magnetization vector, as is shown in this animation. As long as the nuclei precess in phase, the bulk magnetization is the simple sum of the component magnetizations. Next, we move on to detecting the MR signal. That bulk magnetization vector is the source of the MR signal. It represents a 3-dimensional magnetic cloud surrounding it, which is shown in this schematic here. As that 3-dimensional magnetic cloud precesses near a loop of wire, it will induce an oscillating electrical voltage in that coil of wire. The amplitude of the vector determines the amplitude of the voltage, and the precessional frequency determines the frequency of the signal. Recall that when we start the imaging process, the bulk magnetization vector in its resting state is aligned with the main magnetic field. In this orientation, the magnetic cloud that surrounds this bulk magnetization vector, as is illustrated on the left-hand side of the slide, does not have a time-varying component with respect to the coil and cannot induce a voltage in the coil. What we need is the orientation shown on the right-hand side of the slide, where that magnetic cloud surrounding the bulk magnetization vector has a time-varying component around it and is capable of inducing an electrical voltage in the coil. So how do we get from the left-hand side of the slide to the right-hand side of the slide? We do this by exciting the system by imparting energy at the resonant frequency of the bulk magnetization vector, at the resonant frequency of that bulk magnetization vector. This excitation process is now illustrated in this animation clip. We use the same coil of wire to excite the bulk magnetization vector as we do to detect the signal. The energy is imparted at an oscillating frequency equal to the resonant frequency of the system for sufficiently a long period of time such that the magnetization vector changes from its orientation along the Z axis, the vertical axis, to one where it is perpendicular to that axis. This next video will demonstrate how the excitation and detection processes are put together. In this example, the coil of wire is used as both a transmitter and as a receiver. However, the processes can be separated. In this example, they're shown that one coil is being shown as being used for both purposes. As a transmitter, the coil transmits RF at the resonant frequency of the bulk magnetization vector. The vector is tipped from its resting state aligned along the z-axis to an alignment perpendicular to the z-axis, usually referred to as the transverse or xy plane. In this orientation, the vector has a time-varying component relative to the receiver and can thus induce a voltage in the receiver coil, which is shown in the tracing at the bottom. And as you see in the tracing at the bottom, for a reason which I have not yet explained, the voltage decays away in an exponential manner. I will explain that a little bit later in this talk. At this point, we're going to digress for a moment to discuss the rotating frame of reference, a mathematical tool that is very useful to simplify our picture of complex motions. We start in the equilibrium position with the bulk magnetization vector aligned along the z-axis, and it precesses down as an excitation pulse is applied to it. When you look at this motion, it's a pretty complex motion from our frame of reference, so the room frame of reference or the laboratory frame of reference. However, if we position our observational view in the frame of reference of the rotating frame, the motion becomes much simpler. So instead of this complex motion that we observe from our frame of reference, if we look at from the frame of reference of the camera that's rotating with the bulk magnetization vector, it becomes a much simpler motion. The bulk magnetization vector begins completely vertical and comes down in a straight arc into the horizontal plane perpendicular to the z-axis. Let's now go back and look at our four nuclei in an applied external magnetic field and the bulk magnetization field in different frames of reference. What you see here is the nuclei precessing together or precessing in phase, and the bulk magnetization vector precessing at the same rate around the z-axis in the laboratory frame of reference. In the bottom right-hand corner, you see what it would look like in the rotating frame of reference. The frame of reference is rotating, but the bulk magnetization vector is stationary. A way of simplifying this motion, which will be useful as we make our model more complex. We now will look at the signal that is generated in our detection instruments in the laboratory frame of reference and the rotating frame of reference. On the left side, we have the laboratory frame of reference. On the right side, we have the rotating frame of reference. On the left side, every time the bulk magnetization precesses around the z-axis, we get one full cycle oscillation in the signal, and the amplitude is equal to the amplitude of the vector projected on the xy plane. However, in the rotating frame of reference, what we have is the amplitude is constant over the entire measurement cycle, and the amplitude is equal to the projection of the bulk magnetization vector onto that xy plane. The model of four nuclei is now going to be made slightly more complex. We'll keep three nuclei identical. They're colored in red, and they will experience identical magnetic fields. But we'll make one nucleus, the blue nucleus, different in that it will experience a higher magnetic field. This often happens in biologic systems because the nuclei themselves behave like little magnets and cause local perturbations in the magnetic field, causing local changes in the field strength. Some nuclei are experiencing higher field strengths, some lower field strengths. On the right, we will look at what the vector sum of these nuclei is in the frame of reference of the red nuclei. As we start, we see that the blue nucleus is aligned with the 3 red nuclei, and their vector sums will be additive. Let's watch what happens when we play the animation. At certain points of time, the vector is now out of phase, in phase, out of phase, in phase. It will be subtractive, additive, subtractive, additive, subtractive, additive. And as this goes on, the signal that's detected from such systems will go up and down as these vectors go in and out of phase with respect to one another. This often happens when one has hydrogen nuclei that are in fat and hydrogen nuclei that are in water in the same voxel, because they precess at slightly different rates. So over various cycles in the MR imaging process, they will be in phase and out of phase with respect to one another. The model is now made more complex, where all the nuclei in the system are slightly different from one another. In this particular system, it's represented by just 4 nuclei. And in reality, this is the situation in real life. The nuclei may start in phase, but they experience slightly different magnetic fields with respect to one another. So in the rotating frame of reference, they will eventually all be pointing in different directions from one another, and their vector sum will tend towards 0. Let's watch this with this animation. What we see here on the right is, in the rotating frame of reference, each of the nuclei eventually get pointed in a different direction or out of phase with respect to one another, and their vector sum will tend towards 0. The model is now made one more step more complex, wherein all the nuclei are different from one another. We see the nuclei in the upper left-hand corner, their vector representations in the upper right-hand corner, the vector sum of the individual components in the bottom right-hand corner, and the signal that we get in our detector in the bottom left-hand corner. Let's watch what happens as these nuclei get out of phase with respect to one another. In the upper right, you see the vector representations eventually get completely pointed in different directions from one another. In the bottom right, you see the vector sum tends towards 0. And in the bottom left, you see the signal decays away exponentially from its initial maximum, eventually towards 0, in an exponential manner. This is due to dephasing, and it's called T2 star relaxation. There are several MR properties of tissue that affect the amount of signal that one can get from the tissue. In the previous slide, we discussed one of these, T2 star relaxation. And it should be intuitively obvious that the faster the decay process, the less signal that can be detected at any point in time with the detector. There are perhaps 20 to 30 other important properties of tissue that will affect the amount of signal that's obtained from the tissue, but only a few of these will be discussed here. T2 star relaxation has already been discussed. Proton density is the amount of hydrogen nuclei that participate in the NMR process. And again, it should be intuitively obvious that the more nuclei that there are per unit volume, the greater the amount of signal one would get from that tissue. The 2 other properties that I will discuss in this presentation are spin-spin relaxation, also known as T2 relaxation, and spin lattice relaxation, also known as T1 relaxation, recognizing that there are several other important properties of tissue that will not be discussed in this presentation. This slide illustrates the basic steps in the spin echo pulse sequence. There are 5 component pictures on this slide, A, B, C, D, and E. We start with A, with the bulk magnetization vector aligned along the Z-axis, apply an excitation pulse that changes the orientation of the bulk magnetization perpendicular to the z-axis. At this point, the individual components in that bulk magnetization vector, as shown in B, dephase with respect to one another. In C, an inverting pulse is applied to the entire system, such that the component vectors are flipped to the opposite side of the z-axis. In this orientation, the component vectors that are precessing faster than the slower components catch up to the slower components, and everything comes back into phase, as is shown in part D, and what is known as an echo is formed. E illustrates the sequence. First, the excitation pulse, typically a 90-degree pulse. Then at a time later, typically called echo time divided by 2, or TE divided by 2, an inverting 180-degree pulse is applied, and then an equal time later, an echo is formed and a relatively large signal is created in our detector. I am going to use the same schematic as before to illustrate the spin echo pulse sequences and what happens to the bulk magnetization vector as it dephases and as it is inverted. Let's watch the animation. We start with the resting state. We apply an excitation pulse after a period of time. The vector gets deflected down to the XY plane and begins to dephase. We invert it. The faster precessing vectors catch up with the slower ones, come back into phase. We get a strong signal back known as an echo. Let's watch what happens when the time between the excitation and inverting pulse is short, a short echo time, as opposed to a long echo time. With a short echo time, the individual components do not have much time to get a phase with respect to one another. So when they're inverted, they come back better into phase than as is illustrated here with a longer echo time. With the longer echo time, the individual components get more and more out of phase with respect to one another. When they are inverted, they do come back partially into phase, but not as well into phase as with the shorter echo time, so we get a lesser signal. With the spin echo pulse sequence, that inverting pulse can be applied multiple times, but with each echo, the total amount of signal is less than with the previous echo. If one joins the amount of the points at the origin with the peaks of the echoes using this experiment, the quantity that is obtained is called the T2 relaxation time. In comparing T2 relaxation to T2 star relaxation, T2 relaxation is always a slower process than T2 star relaxation because T2 star relaxation is influenced not only by how these magnetic dipoles, the hydrogen nuclei, affect one another, but also by local inhomogeneities. The spin echo pulse sequence removes the effect of most of these local inhomogeneities, and therefore the decay is slower than with T2 star relaxation.
Different tissues in the body have different spin densities and different relaxation times. These differences can be exploited in pulse sequence design to maximize the image contrast between different tissues based on their different properties, and thereby create images with high image contrast, which in MRI is called image weighting. For example, in the head, CSF has a longer T2 relaxation time compared to white matter or gray matter. And when it comes to disease detection, things like tumors, infarcts, infections, and demyelination usually have longer T2s compared to white matter and gray matter. To make these diseases stand out on images with a high degree of contrast, T2 weighted images are very useful. To maximize the difference in signal coming from CSF relative to the signal coming from white matter or gray matter based on T2 differences, the pulse sequence should be designed to wait for a relatively long period of time before the receiver is turned on and the signal is sampled in order to maximize the separation in the T2 decay curves of these tissues. The time between the creation of transverse magnetization with an excitation pulse and the sampling of the signal is conventionally called TE, or standing for echo time. So the excitation pulse would be here, the decay occurs here, and when these curves are maximally separated somewhere in this region here, you would get a T2 weighted images. You would get a T2 weighted image. For T2 weighted images of the head, TEs of about 80 to 120 milliseconds are used. On such a T2 weighted image, as is shown here, CSF will be brightest because it has the slowest T2 decay. Gray matter will be next bright, and white matter will be the darkest because it has the fastest T2 decay of these processes. If one samples the signal too soon after the excitation pulse in this region here, the signal coming from the tissues would be based mostly on the spin density of the tissues, with very little contribution to the difference in signal based on T2 relaxation. So one would have a spin density weighted image. If TE is very long, the signal from all the tissues has decayed away to the point of almost being in the range of electronic noise. So the amount of signal everywhere is very low. The image will be very grainy, and they're diagnostically of poor quality. This slide shows the T2 relaxation times of tissues found within the head. Gray matter typically has a T2 value of approximately 85 to 90 milliseconds, white matter 70 to 75 milliseconds, and cerebrospinal fluid of around 250 milliseconds. Many of the pathologies that we see in the head, such as brain tumors, have T2 relaxation times of 100 to 120 milliseconds. This is true of many other diseases too, like stroke, infection, and demyelination.
The final tissue property that I'm going to discuss in this talk is called T1 relaxation. T1 relaxation describes the regrowth of the magnetization vector back to its equilibrium state after it had been excited downwards out of its equilibrium state. In this animation, we use the same schematic with the resting state of the bulk magnetization vector aligned along the z-axis. We're going to apply an excitation pulse, and then because of dephasing, the vector will decay away very rapidly. What I hadn't discussed up until this point, that while that decay is occurring, the vector is actually regrowing back along the z-axis. Let's watch this animation. Excitation, fast decay, slow regrowth. And as it regrows, it eventually reaches its maximum magnetization in an asymptotic method, which is proportional to its proton density. In the next part of this model, let's create two different tissues, a green tissue and a yellow tissue. In this model, we will give both tissues identical rates of decay, but deliberately give them different rates of regrowth, such that one regrows along the z-axis faster than the other tissue. Let's watch what happens. Excitation pulse. Flip down, decay away rapidly, but the yellow tissue has a faster T1 regrowth than the green tissue. So if we were to flip them back down at this point in time, the yellow tissue would create more magnetization in our detector than the green tissue, because it will have regrown at a faster rate than the green tissue will have regrown. The purpose of this slide is to look at the T1 relaxation process a second time. As shown in the previous slide, we have created a system that has
nuclei with two different relaxation times. The nuclei represented by the yellow bulk magnetization vector has a faster T1 relaxation than the group of nuclei represented by the green bulk magnetization vector. So if we look at their remagnetization along the z-axis prior to their full recovery, the yellow magnetization vector will have greater magnitude than the green magnetization vector, as is shown in the graph on the right-hand side, which is a graph of magnetization along the z-axis versus time. If we expose a system to a radio frequency excitation pulse at the resonant frequency of the system prior to full recovery of the magnetization along the z-axis, it will disturb the magnetization from the resting state and tip them towards the transverse plane. And in the transverse plane, the magnitude of these vectors will be proportional to their magnitude prior to the flip. So, but now they are time varying with respect to the coil, and the yellow vector will induce a higher amplitude voltage than the green magnetization vector, and it will show up as a higher signal intensity on the image compared to the green magnetization vector. This relates to the timing between RF excitation pulses. This is usually referred to as the TR, or repetition time. If the TR is short, by short I mean short relative to the remagnetization of the vectors through the full recovery, they will be flipped down into the transverse plane prior to full recovery, and so the magnetization with the faster T1 relaxation time will create more signal in the coil than the magnetization vector, which has a slower recovery. And what this will create is what we call a T1 weighted image. Because it discriminates between magnetizations that have different T1s. The magnetizations with faster T1s will show up as brighter compared to the magnetizations with shorter T1s. For best T1 weighting, a relatively short repetition time is used, and right after the tip of the magnetizations in the transverse plane, the signal is sampled as fast as possible to minimize the contribution of T2 decay to the amount of signal that is achieved. So to get a T1 weighted image, one wishes to use a relatively short TR to maximize the difference between T1 recoveries, and a short TE to minimize the contribution of T2 effects to the image.
The basic steps in a T1 weighted image are shown in this slide here. We start with longitudinal magnetization aligned along the Z or Z axis. We apply an excitation pulse which creates transverse magnetization. That transverse magnetization decays away, and the magnetization regrows at a certain rate along the Z axis depending on its T1 time. The time between these excitation pulses is called the TR. T1 relaxation differences can also be exploited in pulse sequence design to maximize the image contrast between different tissues based on the differences between the T1 differences between tissues, and create T1 weighted image. To maximize the difference in signal coming from CSF relative to white matter based on T1 differences, the pulse sequence is designed to maximize the difference in magnetization regrowth that has occurred along the Z or Z axis between tissues with slow regrowth, such as CSF, and tissues with fast regrowth, such as white matter, before applying each excitation pulse that will create the transverse magnetization that will be measured with the receiver coil. The timing between these excitation pulses is called the repetition time, or TR, as is shown here. For T1 weighting, the TR should be in this range here.
where the remagnetization curves are maximally separated. The typical TR to achieve T1 weighting is about 400 to 700 milliseconds, but this depends on the field strength of the MRI scanner, because T1 is linearly dependent on the field strength of the magnet. The higher the field strength, the longer the T1. So let's look, we get a T1 weighted image if we use a TR in this range here, and this is a typical T1 weighted image showing here, where the CSF, which has a longer T1, will look darker than the white matter, which has a shorter T1. If we wait too long before applying the next excitation pulse, the regrowth for both CSF and white matter will be at their maximum, which depends on their spin density, not on the rate of regrowth. So we'll end up with an image which is spin density weighted rather than T1 weighted. If TR is very short, for example, in this range here, the amount of remagnetization is very small, and very little signal would be available from all tissues, resulting in very grainy, noisy, diagnostically poor images. So very short TRs are avoided in conventional imaging. Sample T1 relaxation times for the normal tissues found in the head are shown on this slide here. You will note T1 relaxation, which is, I think of as a regrowth of magnetization along the Z or Z axis, is around 10 times slower than the decay of magnetization in the transverse planes. So typical T1 relaxation for gray matter is on the order of 800 to 900 milliseconds, white matter 500 to 600 milliseconds, and CSF around 1900 to 2000 milliseconds, all about a factor of 10 slower than the T2 decay process. Brain tumors, a prototypical disease example that we use, think of in the head, has a T1 relaxation time usually in the range of 800 to 1000 milliseconds.
This slide brings us to the end of part one of this talk, the fundamentals part. What we have discussed so far is magnetization, how that magnetization generates a signal in our detector coil, and we've also discussed which properties of tissue will create higher signal and lower signal. We have not discussed all these properties, but the ones we did discuss was proton density, T2 star, T2, and T1. We recognize that there are many other things that influence the amount of signal that we get. So if we have low proton density or fast decay processes or slow remagnetization, slow regrowth, all these factors will result in low signal in the tissue that we're imaging. If we have high proton density, slow decay processes, or fast regrowth, all these things will result in higher signal in the tissue that we're imaging. But up until this point in time, we have not discussed how we determine where in that tissue we localize the signal. This brings us to part two of the talk, the part on image formation. How is the signal spatially localized and an image created? Up to this point, we have described how we get signal in our detector, various factors that influence the amount of signal we get in our detector, but we have not discussed in any way how we determine where the signal is coming from. We only know that the signal is coming from somewhere in the head. So the signal we're getting is a signal from the whole head. In the next part, we will describe a spatial localization process whereby we can determine where in the head the signal is coming from and ultimately generate an image of the head. There are several subcomponents to part 2 of this talk. These components include a look at the structure of an MR image, spatial frequencies, magnetic field gradients, control of professional frequencies with gradients, collection of data during application of gradients, and reconstruction of the MR image from the data that is collected. First, let's look at the structure of an MR image. An MR image is a digital image that is composed of pixels representing voxels with a certain grayscale in a certain location. MR, like all digital modalities, has the same image problem-solving issue. If one can find the location and brightness of each pixel, then one can create the image. This is true of MR in the same way it is true of CT, ultrasound, nuclear medicine, or conventional X-ray. But the process by which this occurs with MR is different from all these other methods. The issue with MR is that the detector that we place beside the body part that we wish to image, and throughout this talk the example has been the head, how do we localize the signal in the head? Because the detector picks up the signal from the entire head, or at least the part of the head that it is closest to. So the MR signals originate from all tissues, not from a single pixel or a single voxel. The spatial localization task is done in a stepwise process that is dependent on that first equation shown at the beginning of the first part of this talk, the Larmor equation. The way the spatial localization is achieved is by conventionally first defining a slice in the z direction and then finding the pixel location within that slice in the x and y directions. Conventionally, these processes are called selective excitation for the definition of the slice in the z direction, and frequency encoding for localization in the x direction, and phase encoding for localization in the y direction. But they're all dependent on that Larmor relationship, which states that the precessional frequency of the spin is dependent upon the magnetic field strength that it experiences. First, let's examine selective excitation in the z-axis. Selective excitation combines the effects of NMR resonance, magnetic field gradient, and an RF excitation pulse. The model we use is illustrated on this slide, this white cylinder lying on its side with the z-axis running along the long axis of the cylinder. If a excitation pulse is applied to the bulk magnetization vector and the excitation pulse is not the resonant frequency of the bulk magnetization vector, the bulk magnetization vector will not absorb that frequency and will not be perturbed from its resting state. However, if the excitation pulse is at the Larmor frequency of the bulk magnetization vector, the bulk magnetization will absorb that energy and be progressively perturbed from its equilibrium state along the z-axis towards the xy plane. This only happens if the excitation frequency is at the Larmor frequency of the bulk magnetization vector. So in this model, we start with a uniform magnetic field with the body part placed in the center of the MRI scanner, as represented by cylinder here. The field is uniform in each of the x, y, and z axes. Then the field is very precisely and deliberately changed in one direction, conventionally first in the z direction, such that the magnetic field is higher at one end of the cylinder than at the other end of the cylinder. And what this does is it creates a distribution of precessional frequencies at the chin end of the head compared to the vertex end of the head. At the vertex end of the head, where the magnetic field is lower, the precessional frequency will be lower. At the chin end of the head, the precessional frequency will be higher. If at this point an excitation pulse is applied at a certain frequency, only those spins in the slice that match the resonant frequency of the excitation pulse will be perturbed from their resting equilibrium state in the z-axis into the xy plane, and once into the xy plane, they will precess and generate a signal in our detector. Let's watch this animation. We apply an RF pulse in the presence of a gradient. The pulse matches the Larmor frequency of only one location along that direction. That vector absorbs that energy, is perturbed from the z-axis into the horizontal plane, and in that plane we can detect the signal. So only one slice is excited. Only the one excited slice can induce the signal in the coil. Next, we move on to frequency encoding and phase encoding. In many textbooks, these are described as different processes, but in the animations that come next, you will see that these processes are really the same thing. To localize the source or location of the signal in the imaging slice, typically two processes occur: phase encoding and frequency encoding. Usually phase encoding is done first, followed by frequency encoding, but the two processes can be done concurrently. To achieve phase encoding, typically a gradient is applied in the y direction and it creates a phase twist along the y-axis. For frequency encoding, a gradient is applied in the x direction and it changes the precessional frequencies along the x-axis. At this point, let's pause and ask the question, how do we make a picture? How do we draw? This is a painting by Picasso in 1949. How would a person draw this vase with flowers? And how would MRI make a picture of this vase with flowers? Let's first look at how Picasso made this painting. He takes paint on a paintbrush and he adds data to the painting, either one point at a time or one line at a time, but there's no data being added to anywhere where his paintbrush is not. He's making point-by-point additions to the picture until the picture is complete, ultimately ending up with this picture. MR makes pictures in a different way. Rather than adding information to the image one point at a time, it adds information globally to the entire image consecutively over each point in time. But they're global additions, not point-wise additions. And it does this by consecutively adding what are called spatial frequency information across the entire image. But what these resemble in real life is a series of stripes of different intensity, different spacing, and different obliquities. So we have different frequencies of stripes across the whole image, high frequency versus low frequency, different intensities of stripes, and we're going to put these stripes across this image in different obliquities. So the first stripe we add is going to have this obliquity, but it's going to be across the whole image. So we add one stripe pattern across the whole image. And we keep doing this consecutively until the image obtains more and more information of higher and higher spatial resolution. Next, we add information across the whole image with a frequency pattern which is different, at a different angle, a different obliquity, and a different intensity, such that after the addition of the second batch of data, the MR image at this point would look like this. So after 2 additions of data globally to the entire image, this is what the MR image would look like at this point of the reconstruction. This process is repeated multiple times. In this image, the new data that is being added is shown in the bottom right-hand corner of the slide, and the result, once the data is added to the pre-existing reconstruction, the result is shown across the center of the slide. With each successive addition, a different pattern of spatial frequencies is added of a different frequency, a different brightness, and a different angle across the image, or a different obliquity across the image, as is shown here with the addition of the third point of data. Over the next several slides, more and more data of different frequencies, intensities, and angles is added to the reconstructed image until ultimately we get the final reconstruction. This will be illustrated in the series of the next several slides. With each slide, the new data that is being added is shown in the bottom right-hand corner, and the resultant reconstruction at that point in time is shown across the center of the image. After the addition of 100 data points, this is what the image would look like. It's starting to take on a faint resemblance of Picasso's vase. We continue to add more data, but always across the whole image. This is what it looks like after 300 data points. You'll notice that there is data beyond what we perceive as the edges of the vase. That's because this data is being added in a stripe pattern across the whole image. This is what it looks like after the addition of 100 data points across the whole image. 1,000 data points across the whole image. After 5,000 data points across the whole image. And after 64,000 data points across the whole image. One point I would like to make at this time is that the order in which the data is added to the image really doesn't matter. The important thing is that there be enough data of different frequencies, intensities, and angles to be able to reconstruct the image at the spatial resolution that is desired. The order itself doesn't matter. So the image on the left is made by paintbrush by local additions of dots and lines, one point or line at a time, whereas the image on the right, made by the MRI scanner, is by global additions of these stripe patterns across the entire image to achieve ultimately the same image, or at least a very similar image. How does MR imaging make these stripes? How does it make these stripes of various spatial frequency and of variable orientation? and an even more basic question, why has this process been chosen for the way of making MR images? With respect to that last question, is because it is relatively simple to get the spatial frequency information out of the MR scanner at different frequencies and different orientations. The next slides will illustrate how images are made from these spatial frequencies and how these spatial frequencies are created. In most textbooks, when spatial localization is described, it is described as a two-step process, first by changing the gradient in the y direction, and then changing the gradient in the x direction. The same process will be illustrated in this talk, but in a slightly different manner, which I think will make the process more intuitively obvious. To move forward with this model, we are going to change our representation of the bulk magnetization vector from the arrow that we've been using up until this point to a black and white ball, because we're going to make the model more complex, and as we make it more complex and populate our image with thousands of voxels, having thousands of rotating yellow arrows would be too difficult to understand. And graphically, it is much more intuitive if we replace it with the black and white ball, which I shall illustrate here. Here we have the arrow rotating or precessing near our detector. We're going to replace that arrow with a black and white ball. When the arrow is pointing towards the detector, the ball is white. When it's away from the detector, the ball will be black. So the model changes at this point. We're replacing the bulk magnetization vector with a black and white ball, white being positive end of the vector, black being the negative end of the vector. I'm going to use this model of the black and white ball to illustrate the effect of the gradients on the orientation of these balls and their precessional frequencies. First, we're going to look at this in one dimension. In row A, we have all the balls lined up such that the white face of the ball is towards us and the black face of the ball is away from us. And we're going to examine everything in the rotating frame of reference of the ball in the middle of that row, which is the ball with the vertical dashed line through it. In row B, we can see as we apply a gradient to this one-dimensional array, in the frame of reference of the center ball does not change. But as we move progressively to the right, the ball becomes progressively blacker because of counterclockwise rotation as we move towards the edge of the one-dimensional array. And towards the left, the balls rotate in a clockwise direction with respect to the center ball and become progressively more black because of that clockwise rotation. Let's look at the same process with an animation clip as we apply the gradient. The timing of the gradient is shown on the bottom row with the yellow arrow. We can see as the gradient is applied and comes on, nothing happens to the center ball, but the balls that are furthest away from the center ball spin the fastest, but in opposite directions, such that at the end of the application of the gradient, the balls are diametrically opposed to one another. As we continue with the model and look at the model in 2 dimensions, I remind you that the black and white ball represents the net overall or bulk magnetization of the H nuclei, which we also call spins, in a volume of space. The degree of whiteness is equal to the magnitude of the magnetization in that volume of space, and the direction of the white side equals the direction of the magnetization in that point in space. We will now move from 1 dimension to 2 dimension using the same model of black and white balls. A reminder at this point as to what these black and white balls represent. Each ball represents a position in a two-dimensional image. Here we illustrate an array of approximately 10 by 10 balls of a two-dimensional image. We're going to show what the effect of the application of a gradient is on these balls. What you will notice that when we apply a gradient in the x direction in the rotating frame of the center column of balls, the center column of balls do not change their orientation, but as you move towards either the right or left edge of the image, the balls will spin progressively at higher frequencies such that they'll get more and more out of phase with respect to the ball at the center. And what you'll see is a formation of stripe patterns across the image. When the gradient is initially applied, there's just a low frequency of stripe patterns across the image, but at the completion of the gradient, you'll see that there's a complete stripe pattern across the whole image. Let's watch this animation. As the gradient is applied, you'll see the balls begin to spin in different directions with respect to the center. One set of stripes across the image, two threads, 3 sets, 4 sets, 5 sets, 6 sets. You see more and more stripe patterns formed as that gradient's applied for longer and longer. In the previous slide, I illustrated how vertically oriented stripes of any spatial frequency could be achieved across the whole image by applying a gradient in the x direction. This slide illustrates that the same can be achieved with respect to horizontal stripes by applying a gradient in the y direction. Watch the animation. When the gradient is first applied, we get low spatial frequency information in the y direction. As it's applied for a longer and longer period of time, we get higher and higher spatial frequency information in the y direction until we get the maximum at the completion of the application of the gradient. In the previous 2 slides, I demonstrated how vertically oriented stripes could be created across the whole image by using an x gradient, and how horizontally oriented stripes could be created by using a y gradient. In this next animation, I'm going to demonstrate how the application of x and y gradients can be applied in one after the other or together to create obliquely oriented stripes of any orientation at any frequency across the whole image. When these stripes are being formed, the data will be sampled, the data being the total amount of signal created by the magnetization, and that data will be mapped into our data space, which we call K-space or Fourier space, which is shown in the bottom right-hand quadrant of this slide. Let's play the animation. First, we increase the array of balls from 10 by 10 to 100 by 100, and then we're going to apply the x and y gradients. In first pass, only the x gradient is applied, and a pattern of vertically oriented stripes is produced. The data is sampled and placed in one line in K-space. On the second pass, the y gradient is applied at a relatively low amplitude, followed by the x gradient. Stripes of various obliquities are produced of higher and higher frequency, and a second line in K-space is filled with the data. On the third pass, which is the last pass I'm going to illustrate, a higher amplitude y gradient is applied, followed by the x gradient, and another line of K-space is filled. This process is repeated and repeated until all the lines of K-space, all the points in K-space are filled. It would be useful at this point to take a look at how the data is stored. Typically, with MR imaging, the data is stored in Fourier space, which is also known as K-space. And there's a reciprocal relationship between image space and K-space, which I'll illustrate with a succession of slides. The relationship between the two is the Fourier transform and the inverse Fourier transform. If we take a single point in K-space, for example, at the origin of Kx and Ky, that yellow data point represents zero frequency information across the entire image, and the brightness of that data point represents the brightness of the data. A very bright point represents very whiteness in image space. If we take a data point which is along the positive Kx axis, it represents a series of vertically oriented spatial frequencies, or stripes, across the image. The further we get towards the edge of K-space along the Kx axis, the higher the frequency of that information, but it's always vertically oriented. If we take a point that is neither on the Ky nor Kx axis, that represents a series of oblique spatial frequencies or oblique stripes across the whole image. If we take a point along the y-axis, it represents a series of horizontally oriented stripes. So if you look at the typical K-space representation, it looks like a series of dots distributed in the 4 quadrants of K-space. Each of those dots represents a series of stripes of different amplitudes, obliquities, and frequencies. And if all those stripes are added up, as I showed you with that Picasso vase, you will get an image of the head. An important point to understand about Fourier space is that it's related to image space via the Fourier transform. So any dot in K-space, as illustrated by the yellow dot that you see in the image on your left, will create and affect data across the whole image, as is illustrated by the stripe pattern on your image on your right. The reciprocal relationship also applies. To obtain a single point image space requires all of the data in K-space to form that pixel and the information associated with that pixel. At this point, I'd like to combine the information that we learned in part 1 under basic principles and in part 2 under image formation. So before we started the process of image formation, in part 1, after the application of precisely timed radio frequency pulses, the spins in every voxel evolved to a certain magnetization, and thereby were contributing to the signal that we got in our RF receiver coil. So although we couldn't see it in this image of the head, each different points in this image of the head were different degrees of magnetization, contributing a different amount to the total magnetization that we're seeing in a receiver coil. But we didn't know exactly where that information was coming from. All we knew it was coming from the head. In part 2, we applied gradients to localize the signal. This spatially encoded data is digitized and stored for the subsequent image reconstruction, which I'll illustrate in the next animation. In this animation, we see the distribution of voxels in the patient's head, and their magnetization is represented by different shades of gray before the application of the gradients and the spatial localization process. We turn on the gradients, and as the gradients are turned on, we get this spatial information that's distributed, and we get this oscillating signal in a receiver coil The signal is sampled, digitized, and populates one line in k-space. We then apply a gradient along the y direction, followed by the gradient. We get another sinusoidal curve, which the analog signal is digitized, and it populates another line in k-space. We then apply the gradient in y again. We create those horizontally oriented stripes followed by vertically oriented stripes, creating these obliquities. We sample the signal and populate a third line in k-space. We keep doing this until we have all the lines in k-space of sufficient number such that when we reconstruct the image from this spatial frequency data, we get an adequate spatial resolution image of the head. For completeness and correctness, I would like to indicate that we've really only talked about one quadrant in k-space, and many of the slides have been shown up to this point. But we can actually fill all quadrants of k-space using a similar process. K-space has symmetry on either side of the kx and either side of the ky axis. So there are mirror images of one another. How do we scan all four quadrants of k-space? Well, we simply apply gradients in the other direction, as is illustrated in the next group of slides. What we've seen up until this point is simply an application of a positive lobe to the phase encoding gradient and frequency encoding gradient in the following way. Phase encoding followed by frequency encoding, filling one line in the upper right-hand quadrant of k-space. However, by the application of negative lobes, all quadrants of k-space can be filled, as is illustrated here. Add these negative lobes, we get driven down along the negative ky direction and the negative kx direction. Then we can reverse the frequency encoding gradient along x and fill one line of k-space, as is illustrated here. To achieve faster sampling of k-space, the phase and frequency encoding gradients can be applied at the same time, and the trajectory through k-space will look different, as is illustrated here. We apply the gradients at the same time, superimposing them, first in a negative direction, and then in the positive direction. We will fill k-space in the following way. This allows shorter echo times and faster scanning. The most common way of collecting data in k-space is called the Cartesian sampling or rectilinear sampling method. This is illustrated in this animation. On your left, you see 5 lines, the radio frequency, gradient Z, X, and Y lines, and the data sampling line. The time axis is along the horizontal axis. As the timing is played out, you'll see what the trajectory is through k-space. First, the slice selection, negative y, followed by negative x, followed by positive x, fills one line in k-space in the horizontal direction. Second time around, the y gradient is incremented, followed by the x gradient, and this keeps happening until all the lines that are desired in k-space are achieved to get the spatial resolution that you want in your image. This is by far the most frequently used method of data collection and filling of k-space. And the total scan time is equal to the number of phase encodes multiplied by the time interval between the phase encodes, which is called the repetition time. There are different ways of collecting data in k-space using different timings of the gradients. These are used for different purposes, and by and large are used for specialty purposes in niche uses. One of these is called radial sampling, which I will illustrate here. And this radial sampling, the X and Y gradients are applied at the same time. So the trajectory through K-space is always through the origin using this radial pattern. So there is no real phase encoding gradient, only frequency encoding, and both frequency encoding gradients are applied at the same time. It allows for faster scanning. A third method of collecting data for K-space is something called spiral sampling. This is the last sampling method that I'm going to illustrate. And what they do here is they oscillate the X and Y gradients such that K-space is filled in a pattern of spirals. But in every one of these K-space strategies, the objective is to achieve enough K-space points to get the spatial resolution that one wishes in the image that is being in the imaging that is being performed. Let's watch the trajectory through K-space with spiral sampling. See, an oscillating X and Y gradients, sampling as one goes, different oscillation patterns until all the data that one wishes is achieved. And ultimately, you get fewer trajectories needed for the types of specialty scanning in which this is used, and get overall faster scanning. So up until this point, as far as image formation is concerned, we have placed the patient's head in the center of the scanner. We have applied a series of excitation pulses, detected the signal in the presence of gradients, and collected that data in K-space. In the final 5 minutes of this talk, I'm going to show how that data in K-space is reconstructed and an image formed. In this final segment, I will show you how the data is taken from K-space, remembering that these dots in K-space represent spatial frequencies across the whole image, how that data is reconstructed, and how the image is formed. I want to orient you to this animation before I play the animation. In the bottom left-hand corner, you have the K-space data that is going to be used to reconstruct the head in the upper left-hand corner. So the data in the bottom left is the same as the data in the upper left, and the relationship between the two is the Fourier Transform. The image on the bottom right is something I call stripe space, and it is the pattern of stripes that is represented by the red dot on the image in the bottom left. The image in the upper right is the sum of all the stripes as we add them together before we get to the final image. So now I'm going to play the animation. Watch the red dot. As the red dot traverses from across the KX axis, we can see the stripe pattern become of lesser and lesser frequency until it reverses at the origin and becomes of higher and higher frequency until it gets to the end of the other end of K-space. We now turn on the Y gradient, and now we have a series of oblique stripes. We can see them being added to the image in the upper right-hand corner. The obliquity reverses as we cross the origin, and the frequency of the oblique stripes gets greater and greater. We're going to do this one more time at a higher Y gradient amplitude, showing a greater obliquity of stripes. Again, reverses as we cross the origin. The obliquity reverses, and at this point in time, what we see in the upper right-hand corner is the sum of the data reconstructed from 3 lines of K-space. You can see it doesn't look anything like the final image of the head, which is reconstructed from 128 lines of K-space. Continuing with this process, one point at a time, would take a very long period of time. So in the next animation, I'm going to do the same exercise, reconstructing the data one line at a time. The layout of images on this slide, on this animation, is exactly the same as on the previous slide. However, the reconstruction will be done a full line at a time, starting at the bottom of K-space. The images to pay most attention to are that on the bottom left, which shows which lines of K-space are being added to the reconstruction, and the image on the upper right, which shows the result of the reconstruction at any point in time. Let's play the animation. As you watch the animation, you'll see as we fill from the bottom of K-space, we basically see only edge data, and that's true almost till we hit the middle of K-space, and right after the middle of K-space, we get a lot of signal. Most of the signal is in the middle of K-space. As we go on beyond the middle of K-space towards the opposite end, the image changes very little. It gets progressively better, but the total amount of signal does not change very much. Let's watch this one more time as we cross the middle of K-space. Bottom quarter, bottom 40%, cross the center, lots of signal, almost have the complete image, gets better and better signal and noise and edge information, but the image contrast does not change very much. In this slide, I'm going to do the opposite reconstruction. I'm going to start with the data in the center of K-space and reconstruct towards the periphery. I did not have a good example of this for any of the head imaging that I've done, so Gerhard Lab kindly lent me this image. It's a reconstruction of the aorta, renal arteries, and the kidneys. You can see that if we take only the middle 5% of K-space, we get reasonably good signal where we can recognize the aorta, the renal arteries, and the kidneys, but the edge information is poor. As we add more and more data going towards the periphery of K-space, the total amount of signal does not increase very much, but the edge information gets much better because the periphery of K-space is where this edge information resides. So to conclude, MRI signal is an induced voltage in the coil. The voltage is induced by a rotating magnetic field. In the examples we use today, it's the hydrogen nucleus. The amount of signal is determined by multiple tissue properties, including proton density, T2 star, T2, T1, other things we didn't discuss, and the pulse sequence timing. Localization is achieved by applying radio frequency excitation, pulses, and magnetic field gradients. The data that is achieved is stored in a K-space representation. K-space is the same as Fourier space. The points in K-space represent stripes across the entire image, or spatial frequencies across the whole image. The stripe spatial frequency and orientation is defined by the gradient areas that are applied. The position of K-space points is determined by the amplitude of the applied gradient multiplied by the length of the time that the gradient is applied. In other words, the integral of the gradient over time. The amplitude of the K-space points is determined by the amplitude of the RF signal in the detector at the time the signal is sampled. The center of K-space is where most of the signal resides and therefore where most of the image contrast resides. The edges of the K-space contain most of the object details. Thank you for your attention.